Welcome to 7.2, Simplifying Radical Expressions. We're going to use the product and quotient rules for radicals to simplify radical expressions. Now, we've already learned those in the last section. We're going to use rationalization techniques to simplify, and we may not get to the Pythagorean theorem in application problems, but you did see that in geometry. So just a reminder of the perfect square numbers: 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. And it gives you what number squared is equal to that perfect square. Those will come in handy this chapter. Also, perfect cubes come in handy. We use them a lot. So we have 1, 8, 27, 64, 125, 216, 343, 512, 729, 1,000, 1,331, 1,728. So that's 1 through 12 cubed. So let's start off by the product and quotient rule. If we have this square root of two numbers being multiplied or two expressions being multiplied, then we can break it up into the nth root of one of your products and the nth root of the other product. Same goes for quotients. So if you have a fraction underneath the radical, you can split your radical up into the top and the bottom of your fraction. Let's start by simplifying these radicals. So what we want to do is find a perfect square within 75. So two numbers that multiply to 75 would be 25 and 3. If I multiply the square root of 25 times the square root of 3, I would get back the square root of 75. Well, the square root of 25 is a perfect square. The square root of 25 is just 5, and I cannot break the square root of 3 up. There are no two numbers that multiply to be 3 besides 1 and 3. So I can write the square root of 25 as these bottom tree branches here. 5 and the square root of 3. 5 times the square root of 3. This is simplified form. Let's go to the middle. I don't know off the top of my bat what two numbers multiply to be 100 or 1,167 or 76, but I do know that it's divisible by 2 because it's an even number. And so when I divide 1,176 by 2, I get 588 and obviously 2. So the square root of 2 times the square root of 588 would get me back up here. Now I can't break the square root of 2 anymore, but I can break 588. It's an even number. So again, I have the square root of 2, and now it's 294. So 2 times 294 is 588. I'm going to keep going. It's an even number again. So 2 times 147. This isn't an even number, so I'm going to check my calculator of 3. So I type 147 divided by 3, and it is divisible. There is not a decimal answer. So I get 49 times 3. Now the square root of 49 is a perfect square, which is what I want. The square root of 49 just breaks up into 7. 7 squared would get me 49. I can't break up the square root of 3 or any of these square roots of 2. So I have 7 outside my radical, and all of these are being multiplied. So the square root of 3 times the square root of 2 times the square root of 2 times the square root of 2. So let's see what that looks like written out. Now I can actually combine some of these. So like say my 2 square roots of 2, that can be written as the square root of 2 squared, correct? Because it's something times itself, I can write it as squared. Now remember from the previous section, my square and my square roots cancel. So anytime you have 2 of something, it simplifies to just that number under the radical. So now I have a 7 outside my radical, a 2 outside my radical. I can multiply them because they don't have a radical. So I get 14. And my 2 items that do have a radical, 3 and 2, I can multiply them. So I get a square root of 6 and a 14 for my final answer there. Let's break down 162. You can pause and do this one on your own if you would like to try and see if you get it correct. So your final answer here should have been 9 square roots of 2. That was kind of an easy one. When you divide it by 2, you get the square root of 81. Well, the square root of 81 is just 9. So those previous 3 examples only had numbers. So let's throw in some variables because this is an algebra course. So let's remove variable factors from these radicals. We're going to simplify this expression. Same thing. I want to think about my product rule here. It's 25 times x squared. So I can split this up into the square root of 25 times the square root of x squared. Now the square root of 25, that simplifies to 5. And the square root of x squared simplifies to the absolute value of x. So hopefully you remember from last section that if n is even, then the nth root of a to the n equals the absolute value of a. So these n's match. Remember, I have a square out here. They match and they're even, so we have to write the absolute value of whatever's being squared or to the 4th or to the 6th, whatever that is. Let's hop down here. I have the square root of 12 times x to the 3rd. So what I have going on underneath my radical are 2 things being multiplied. 12 times x cubed. Now, since this is a square root, I want to break up my radicand into perfect squares, so that way they cancel with the square root. If I break up 12 into numbers that are perfect squares, let's just think about it like we were doing in our factor trees on the previous slide. 2 numbers that multiply to 12 are 4 and 3. The reason I picked 4 and 3 is because 4 is a perfect square. It just breaks down into 2. So if I think about it, I can write 12 as 2 squared times 3. And that's what I have going on here. So 2 squared would give me 4 times 3, I'm back at 12. Now x cubed can be broken up into a perfect square as well. X squared times x. If I multiplied them back, I'd get x cubed. So now that I've written it as squares, let's simplify this. So the square root of 2 squared times the square root of 3 times the square root of x squared times the square root of x, because this is a product rule. So my square root cancel. Square root of 3 does not cancel. Square and square root cancel here, so that's the absolute value of x. And it does not cancel with the square root of x. So simplified form, I want to combine everything that's under the radical. So I have a square root of 3 and a square root of x, that's 3x. And everything outside of my radical is 2 times the absolute value of x. The square root of 144x to the 4th. Think about 144 as breaking it up into your factor trees. The square root of 144, if you remember from slide 2, 144 is just 12 squared. So it just breaks down into 12. So writing this under our radical, we have 12 squared times x squared times x squared. So x squared times x squared would give me back to x to the 4th. 12 squared would give me back to 144. So I haven't changed the problem at all. So I have 12 squared times the square root of x squared times the square root of x squared again. My squares and my square root cancel, so I'm left with 12 times x, absolute values. And what I get is 12x squared. This is like x times x, so I get x squared. Last one, 72x cubed and y squared. The variable part is easy to me. I can write x cubed as x squared times x, and I want to leave y squared as y squared. Remember, we're trying to get perfect squares underneath our radical. So I'm trying to think of what 72 breaks down into so that it is a perfect square. And if you type in your calculator, if you pull out 72, you could do 36 and 2. The square root of 36 and the square root of 2. Square root of 36 is just 6. So I found a perfect square here. 6 squared is 36. Times 2 would give me back to 72. So I have 6 squared times the square root of 2 times x squared times x times y squared. I want to break this up using my product rule. Square root of 6 squared times the square root of 2 times the square root of x squared times the square root of x times the square root of y squared. Remember, our square and our square roots cancel, so we're left with 6. Square roots of 2, square and square root cancel, and square root of x, square and square root cancel. We just want to make sure that we write everything that's underneath our radical, multiply it inside your radical. So the square root of 2 and the square root of x, I can multiply 2 times x. Everything outside I want to multiply, I have a 6 times an x times a y for my final answer there. More removing factors from radicals. So I have the cube root of 40. Obviously 40 is not a perfect cube and we don't want this to be a decimal answer. So what we need to do is break up 40 so that we can write it as a perfect cube underneath our radical. So let's think of the perfect cubes that are in 40. So if you go back up here and think about your perfect cubes, obviously anything 4, 5, 6, 7, 8, 9, 10, those are over 40, so we're not going to be looking at those. 27 I can't multiply by to get up to 40, but 8 I can. So if I split this up, 40, I can write it as 8 times 5, right? 8 times 5 is 40. So I haven't changed the problem at all. But now using my product rule, this is the cube root of 8 times the cube root of 5. Well, the cube root of 8, that's a perfect cube, and I get 2 there. I can't cube 5, and it's a prime number, so I can't break it down any further. I have 2 times the cube root of 5 for my final answer. Let's try this next one. So your index tells you what you're trying to rewrite your radicand as. So I have an index of 4, so I want to write my radicand as 4th powers. Well, with a variable term, it's kind of easy because that would be x to the 4th times x, right? When you multiply in the same base, you add their exponents. So 4 plus 1 would give me back to x to the 5th. So splitting this up, I have the 4th root of x to the 4th times the square root of x to the, the 4th root of x to the 1st. A 4th root and a power of 4 would cancel. Remember, they're even and they're the same number, so I want the absolute value of x. And there is no 4th root of x to the 4th, so I'm going to multiply it next to it. down here, I have an index of 5. So I want to try to write everything underneath my radical as powers of 5. 486 is kind of a big number. So off to the side here, I just want to work with the 486 because I already know that I can break up my x to the 7th as x to the 5th times x squared. So let's work on the number 486. Well, divide that by 2. These are 5th roots. So you get the 5th root of 2 times the 5th root of 243. 243 is divisible by 3, so you get the 5th root of 3 times the 5th root of 81. 5th root of 81, I can break up into the 5th root of 9 times the 5th root of 9. I can't break up 3 anymore because it's a prime number. 9 can be broken up into the 5th root of 3 times the 5th root of 3. Same thing with this 9. 5th root of 3 times the 5th root of 3. Okay, so that's quite a bit. Let's write this out in long terms. I have 5th root of 2, a 5th root of 3, a 5th root of 3 again, another one, and 2 more. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I did them all. So all of these 5th roots of 3, since they're being multiplied by each other, and there are 5 of them, I can write this as the 5th root of 3 to the 5th power, right? 1, 2, 3, 4, 5. That means to the 5th power if it's times itself. And then I have a 5th root of 2 being multiplied. So my 5th root and my power of 5 is going to cancel, and that leaves me with just a 3. So I have a 3 times the 5th root of 2, which means that 486 can be written as 3 to the 5th power times, I'm sorry, let me back up. Oops, not that far. We already broke down 486 to the 5th power. We got 3 in the 5th power of 2. And we know that our variable was broken down into x to the 5th times x squared. So working on this, if I split that up, I get the 5th root of x to the 5th times the 5th root of x squared. Power of 5 and the 5th root cancel. So I have an x outside my radical. So I'm going to multiply that by the 3. So I get 3 times x. Inside my 5th root, I have a 2 and an x squared. So let's draw our 5th root. 2 times x squared goes in it. Now, the cube root of 128, x cubed, and y to the 5th. So we're looking for perfect cubes here. If we think about breaking 128 down, just the number itself, if you divided it by 2, you'd get 64. So the cube root of 64 times the cube root of 2 would give me back to the cube root of 128. Now, 64 is a perfect cube. It breaks down into 4, which means 4 times 4 times 4 would give me back to 64. So this can be written as, just the number part, can be written as 4 cube roots of 2. Now we have to work on our variable part. It's the cube root of x cubed and y to the 5th. Well, x cubed is already a perfect cube, but y to the 5th isn't. So our exponent of 3 and our our index of 3 is going to cancel. So that would leave me with x outside the parentheses. So I have 4 and an x outside my radical. I have the cube root of 2 inside. And I want to rewrite x or y to the 5th as y cubed times y squared. Now my cube root and my cube will cancel. So y will be by itself. So I have 4 times x times y times the cube root of 2 times the cube root of y squared. If they're the same root, I want to multiply them. So 2 times y squared underneath the cube root would be 2y squared. All right, now this looks like quotient rules since I have fractions. Remember, I can break this up. So if it's the square root of 81 over 25, that means it's the square root of 81 over the square root of 25. These are both perfect square numbers. The square root of 81 is 9 and the square root of 25 is 5. So 9/5 is my final answer. Over here, sometimes you don't want it split up because I noticed that if this were all one fraction, I could simplify the 56 over 8. So I'm going to break this back into the square root of 56x squared over 8. Okay, so I kind of undid what I just did up top. And if I simplify this fraction, 56 and 8 just simplify to 7, and I'm left with an x squared with it. So using my product rule, I can split this up into the square root of 7 times the square root of x squared. I cannot simplify the square root of 7, but on my x squared, remember a square and a square root cancel. The index is the same as the power, and they're even, so that's the absolute value of x times 7. Down here, nothing in my fraction simplifies, so I'm going to break this up. I'm going to leave my negative out in front. So I have the cube root of y to the 5th in my top fraction, and the cube root of 27x cubed. So in my numerator, I'm looking for perfect cubes. So I'm going to write this as the cube root of y cubed times y squared. In the denominator, I'm going to use my product rule to write this as the cube root of 27 times the cube root of x to the 3rd. So in my top, remember my y cubed and my cube on cube root is going to cancel. It's going to leave me with y, but I still have the cube root of y squared. In the bottom, the cube root of 27. Remember 27 is a perfect cube, so that'd be 3. And the cube root of x to the 3rd is just x. So my final answer there. Don't forget the negative out in front. Okay, rationalizing denominators means that no radical can contain a fraction. So like in part A, this radical has a fraction underneath it. That's not okay. No denominator of a fraction contains a radical. So like check out these denominators. They have a radical in them. That's not okay either. So we need to do what's called rationalizing the denominator. So just like before, we're going to break this up into the square root of 3 over the square root of 5 because this fraction cannot be simplified. How am I going to get rid of this radical in the denominator? Well, what I'm going to do is multiply by 1, but it's a funky looking 1. So remember how anything over itself is 1, just like 4 over 4 is 1. Well, we're trying to get our denominator to not have a square root. So if I have a square root of a perfect square number, that would eliminate the square root, right? If I had the square root of 36, that would just be 6. It eliminated the square root. So what can I multiply the square root of 5 by so that it is a perfect square? Well, let's look at our perfect squares. I can't multiply 5 by anything to get me 9. I can't multiply it by anything to get me 16. But I can multiply it by something to get me 25. 5 times 5 would move me up to here. So I'm going to multiply by the square root of 5. If I just multiplied it by a regular 5, then it would be 5 times the square root of 5, and that doesn't help me at all. So I need to multiply it by the square root of 5. And actually, I'm going to do that in red. Okay, so remember how we said we're going to multiply by 1? Well, what do I need in the numerator? I need the same thing, so I'm going to multiply by the square root of 5 in the numerator as well. So I'm multiplying by 1, which means I'm not changing the problem at all. The square root of 3 times the square root of 5, since they're both in houses, I can multiply them. That's the square root of 15. Down here, same thing. They both have a radical. So I multiply them, I get the square root of 25. Simplify this. I'm only concerned about the denominator. I'm not really worried about breaking down 15. So the square root of 25 is just 5. And now I'm good because I don't have a radical in my denominator. Also, there is no fraction inside my radical. There's only a number 15, so this is rationalized. Down here, I have 4 over the cube root of 9. And what's wrong with this is not the fraction part, but the fact that there's a radical in the denominator. So it's a cube root of 9. So what can we multiply 9, the cube root of 9 by to get it up to a perfect cube? So let's look at our perfect cubes here. 9, I can't get it up to 8 or 1. 9 times 3, though, would give me 27. So I'm going to multiply it by 3, but not just a regular 3, because that wouldn't help us at all. It's got to be the cube root of 3 so that I can multiply these numbers. If I multiply it in the bottom, I have to multiply it by in the top. So in the top, doing that, I can't combine those, so it's just 4 times the cube root of 3. In the bottom, I can combine them because they're in the same radical. So 9 times 3 give me 27, and it's being cube rooted. Can't simplify my numerator, but in my denominator, the cube root of 27 is just 3. Last one for this page. I have 3 times the square root of 18. It's not the cube root of 18, it's the square root. So I need 18 to be a perfect square. What can I multiply 18 by to get one of these perfect square numbers? Well, nothing to get me 25, but if I take it times 2, I'd be at 36. So I want to multiply by 1, but it's a funky looking one. I'm really not concerned about the 3 because it doesn't have a radical on it. So what I do want to multiply that by is the square root of 2 in the top and in the bottom. I would make my numerator 8 square roots of 2. My denominator would be 3 square roots of 36. I can only multiply if they have the same radical and they're both squared, so I multiply the numbers, leave it under the radical. Numerator does not simplify. Denominator, the square root of 36 is just 6. So I have 3 times 6. I'm going to simplify that to 18. Now notice that your 8 and your 18 can be simplified. If you divide them both by 2, you'd get 4 and 9. So final answer is 4 square roots of 2 over 9. Rationalized and simplified. Last two. We have a fraction underneath our radical, so we need to fix that. I'm going to split this up into the square root of 8x over the square root of 12y to the 5th. And actually, before I do that, I do notice that I can simplify my 8 and my 12. If I divide them both by 4, I'd get 2 and 3. So now I have the square root of 2x over the square root of 3y to the 5th. Okay, I simplified it and then I broke it up into two radicals there. So we're concerned about this denominator. I need to write them as a perfect square as best I can. So I'm going to have to multiply by numbers and letters. What can I multiply 3 by to get it into a perfect square? It looks like I could get it up to 9 if I multiplied by 3. So I know I'm multiplying by a square root of 3, but I also need to be concerned about y to the 5th. If I multiplied by one more y, that would give me y to the 6th. And y to the 6th I can break up into several y squares, so I'm good with y to the 6th having that underneath my radical. So I've multiplied by 3y in the bottom, I need to multiply by in the top to make sure everything's staying even here. When I do that, I'm going to multiply my numbers together since they're both underneath a square root. So I get 6 and x times a y in the top. Down below, they're both under the square root, so I can multiply numbers. 3 times 3 would be 9. Y to the 5th times y to the 1st would be y to the 6th. Let's keep working on simplifying our denominator so that it doesn't have a radical. Oops, that's supposed to be a 6. Remember, that's our goal, no more radical in the denominator. So let's break this up into the square root of 9. And I'm going to break up y to the 6 into y squared times y squared times y squared. Remember, those would give me back to y to the 6, and they're all underneath the square root here. So my top is fine. It can have a radical. My numerator can have a radical, but my denominator can't. Square root of 9 is 3. Y squared to the square root would just be y. And I get another y, and I get another y. So these are all being multiplied. So what I have in the denominator is 3y cubed. Numerator is 6 times x times y underneath the square root. This is rationalized because I have no more radicals in my denominator. Let's look at the last one. The cube root of 54x to the 6y cubed over 5z squared. I can't simplify the 54 and the 5, so let's go ahead and break this up. The cube root of 54x to the 6y cubed over the cube root of 5z squared. Notice I keep my z's and my 2 separate by putting a line through the z. I'd recommend you start getting in the habit of doing that as well. So I'm trying to work on breaking down my denominator into perfect cubes. So what can I multiply 5 by to be a perfect cube? So looking at your perfect cubes, I can't multiply it by anything to get 8 or 27 or 64, but I can multiply it up to get up to 125. If I multiplied it by 25, it would give me 125. So let's multiply by the cube root of 125. And I need one more z to make that z cubed. So I'm going to multiply by another z. What I do in the bottom, I have to do in the top. Let's simplify this. want to multiply everything underneath. Ooh, need my calculator for that. Let's do the bottom first. I'm sorry, I should have multiplied by 25 like I said. Multiplying by 25 z would give me 125. And 25 z in the top. Okay, now we're ready. Denominator, cube root of 125 z cubed. In the numerator, 25 times 54 is 1,350. I have x to the 6th, y to the 3rd, and z to the 1st. Simplify your denominator. Cube root of 125 times the cube root of z cubed. Those are going to simplify to 5 times z. Now I just need to work on simplifying my numerator. I have the cube root of 1,350, x to the 6th, y cubed, and z. So off to the side, let's figure out what 100 or 1,350 would break into. If I divide it by 2, I get 675. And looking back, 675 is not a perfect cube, so I want to keep breaking it up further. 675, let's go divided by 5. And I get 135. If I look back, 135 is not a perfect cube either. By the way, these should all be cube roots since we're cube rooting it. 135, let's go divide by 5 one more time. I get the cube root of 27 times the cube root of 5. So 1,350 can be written as the cube root of 27 cubed times, I'm sorry, let me back up. I didn't finish my factor tree. The cube root of 27 breaks up into 3. So I have 3 times the cube root of 5 times the cube root of 5 times the cube root of 2. Simplifying these would give me the cube root of 25 times the cube root of 2 times 3. Multiply the 25 and the 2, you get the cube root of 50. So that was just my number part. I have 3 cube roots of 50, but I'm also taking the cube root of x to the 6th, y to the 3rd, and z. So let's work on our numbers. Our variables. I still have 3 and then cube root of 50 for my number. And I can break this up, this x to the 6th, into the cube root of x cubed and the cube root of x cubed again. And when we add those exponents, it would give us back to x to the 6th. We still have the cube root of y cubed. That's going to cancel. It's already a perfect cube. And I'll squeeze it in the cube root of z. So let's simplify that. My cube and my cube root cancel, so that would be an x, another x, a y, and then a cube root of z since that doesn't simplify. Denominator is already simplified good. Numerator, I can combine my y's, or sorry, my x's. And that'd be x squared times y times the cube root of z. Let's combine our cube roots and write everything that doesn't have a radical out in front. So I have 3x squared y and the cube root of 50 and times z and 5z in the denominator. Remember, nothing cancels in my top and my bottom. No numbers cancel, no letters cancel. Can't cancel my z's because one's being cubed root and the other is not. So that'd be my final rationalized and simplified answer.